Hello, 8th graders. Mr. LaBeouf here with a continuation of systems of linear equations, but we're going to take a trip back to Chapter 4. We're going to see how concepts from Chapter 4 and skills from Chapter 4 can be understood in terms of Chapter 5. I have two systems of linear equations on the board here. In each system, there is one line is the same in each system. Negative 2x plus 3y equals 5. That's, of course, is in standard form. And in the first system, we have the other equation, x equals 0. And in the second equation, the second system, the other equation is y equals 0. Well, these are both very simple to solve by the substitution method. We substitute 0 in for x here. And we can do this entirely mentally and get y equals 5/3. So the point 0, 5/3 is on this line because 0 and 5/3 make a true statement. And let's solve the other one by the same method of substitution, this time substituting 0 for y. And when we substitute 0 for y, this term goes away. We get negative 2x equals 5, so x equals negative 5/2. This is a point, going back to the first system, this is a point that is on both of those lines. It's on the line x equals 0, and it's on the line negative 2x plus 3y equals 5. So it's the solution of the system. It's the intersection of two lines. And over here, in a similar way, this point, negative 5/2, 0, is a point that's on both lines. It is on the line y equals 0, and it is also on the line negative 2x plus 3y equals 5. So we have solved two systems of linear equations. But we already did this in Chapter 4. We didn't think of it as a system of linear equations, but this is a Chapter 4 topic, which we've been doing for a long time. We found in the first system the y-intercept. Do you recall that when x is 0, you're on the y-axis? And in the second system, we found the x-intercept of the line. Because when y is 0, you're on the x-axis. The axes are lines in the plane. They're obviously special. They kind of like establish the plane, but they're just ordinary lines in the plane. We call this horizontal axis x, that's its name or its label, but its equation is y equals 0. And we call the vertical axis y by tradition, but its equation is x equals 0 because it's a vertical line. Every vertical line is in the form x equals a number, including the y-axis. And as far as the x-axis is horizontal, and every horizontal line has an equation in the form y equals a number. I've taken the liberty in advance of plotting the two solutions of these two linear systems, right? This is the point 0, this is the point negative 2.5, 0. And this is the point 0, 5/3. And this is a very rough graph here, but it does the trick. And so we found the two intercepts, the x and y intercept, and we could have used that skill of finding those two intercepts to graph the line the way I just did. But we're seeing it in terms of two systems of linear equations. So how do we do that? Well, this line is common to both systems, and let's look at this system here where x equals 0. Well, x equals 0 is the y-axis. So let me trace over the y-axis, and we see that the y-axis, which is x equals 0, intersects our line of negative 2x plus 3y equals 5 at that point, which we call the y-intercept. And in a very similar way, when we look at this x-intercept, which is -5/2 or -2.5, 0, we can, now I will trace over the x-axis, and we see that what we know as this x-intercept is a solution to a system of linear equations. This line here and the x-axis, they intersect at that point. So that's kind of a cool thing that is a very common phenomenon in math, where we learn something and then later on we learn something else, and we can put the first thing that we learned into a different context, understand it in a different way, understand the whole picture of math more deeply. And that's something that I always encourage you to do. And talk about going back to basics. This is also a system of linear equations. I would suggest it's impossible to imagine one that's more simple. What is the solution to this system of linear equations? Well, of course it's this. The point 3 comma -2. X equals 3 is a line. It's a vertical line. Y equals -2 is a horizontal line. Where do they intersect? They intersect at the point 3 comma -2. So we can even understand the plotting of points. You see, any teacher that has in mind teaching chapters 4 and 5 of the Algebra 1 textbook, teaching about linear equations and their graphs, which is chapter 4, and systems of linear equations, which is chapter 5. Any teacher that has that in mind, I have the luxury of teaching students from grades 5 through 8, and I know that at some point, usually in 6th grade, I need to make sure that students know how to plot points that in the x and y coordinate plane. That's the #1 foundational skill for everything that comes later on that involves the x and y coordinate plane. It's all about graphing those points, you know, the x coordinate and the y coordinate, all of that. Well, we can understand this now, just as with the previous couple of systems involving the x and y intercepts. We can understand every single point in the plane as being the solution to a system of linear equations. Let me pause for a moment to make a graph. So here is the 6th grade skill. When I teach, first begin teaching about the x and y coordinate plane, of course I emphasize that it's always x comma y, and that's easy to understand, easy to remember. I'm sure that René Descartes or whoever else was involved in establishing this system. René Descartes was a French philosopher and mathematician who's often given credit for establishing what's sometimes called the Cartesian coordinate plane, after his name, Descartes. I'm sure that he or whoever else popularized this made the letters in alphabetical order. You know, that would make sense if you were establishing the way it all works. I'm sure you'd do the same thing. And x, of course, the x coordinate tells us where we are right to left, and the y coordinate tells us where we are up and down. So we teach students, you know, start at the origin, which of course is 0 comma 0, and for the point 3 -2, we go 3 to the right and down 2. 1, 2, 3, 1, 2. 3 to the right and down 2. So there it is. But now we see it in the following way. This is the solution to a system of linear equations. The first equation is x equals 3. That is a vertical line, like this. And of course, that's often the second thing that I get into with teaching about the coordinate plane, is that when you have an equation x equals a number. It's a vertical line. It might seem backwards, but it makes absolutely sense, total sense. Every point on this vertical line has an x coordinate of 3. And, of course, this second equation, y equals negative 2, is this horizontal line here. So I teach that equations that are in the form y equals a number are horizontal lines. It might seem backwards because of the fact that the x-axis is horizontal, the y-axis is vertical, but every single point on that horizontal line there has a y coordinate of negative 2, so the equation perfectly describes the line. And of course, the two lines intersect at that point 3, negative 2. So what we can do is we can understand every single point in the plane as the solution to a system of linear equations where one of the equations is a vertical line and the other equation is a horizontal line. It's awesome. In Chapter 5 of the Algebra 1 textbook, we're about halfway through the course, halfway through a high school algebra course, but something in that chapter can take us all the way back to understand something that we learned in 6th grade in another way, in a deeper understanding of everything that's going on. So there are a couple of little things to start this video, and now we'll move on to a topic which needs to be covered in Chapter 5. So we will get to that. Here is a system of linear equations, and by the way, we're covering now what your textbook authors call special systems, and there are 2 types. This is one. This is a system of linear equations. Let's ignore the obvious for a moment and approach it the way we do systems. The substitution method seems pretty easy and the obvious thing to do here. Substitute 2x minus 1, which is y, for the y here, and we get 2x minus 1 equals 2x minus 1. Now, when I am teaching the solving of equations to even 5th graders, or certainly 6th graders and 7th graders, we usually spend a long time solving equations that have a single solution for x before we talk about the fact that 2 other things can happen. So the question becomes here in this equation, what values of x will make a true statement? And it should be pretty obvious to you. Any single number x, any real number x that we put here, and we also have to put the same number here, of course, in the same equation, each x has to be the same number. Any x that we put there will make a true statement. If we were dealing with this equation just by itself, not in connection with lines, we would say that it is an identity, or that all real numbers are the solution, okay? But in terms of a system of linear equations, well, we go back to the 2 lines, and we see, obviously, they are the same line. And so what we do with systems like this is we say that there are an infinite number of solutions. Every combination of x and y that works here also works here, and the 2 lines are right on top of each other. Infinite number of solutions. Not every point in the plane. In this equation here, x can be anything, but when x is a particular number, the y is a particular number. So in other words, when x is 2, the y is 3. The point 2, 3 is on this line, or these 2 lines. But the point 2, 4 is not, right? So it's not every point in the plane, but there are an infinite number of solutions to this system, because each line, or the same line, has an infinite number of points. So that's another thing that can happen when we're solving systems of linear equations. It can happen that we really only have one line. And the conclusion when that's going on is that the system has an infinite number of solutions. Every point on one line is also on the other because they are identical lines. But you may be saying to yourself, well, this is too easy, this is obvious. Well, let me do something now to kind of show you how this little game is played. Here is a system of linear equations, ladies and gentlemen. The first equation is in the slope-intercept form, and the second equation is in the standard form. And we know how to solve this. The most direct way, I think the easiest way to solve this system, is to the substitution method, to substitute this 2x minus 1 for that y, right? We've seen this before, we've done this. So we'll take this and put it in for y, and the new version of our second equation becomes negative 6x plus 3 times 2x minus 1 equals negative 3, and of course we have to put the 2x minus 1 in parentheses and use the distributive property. So let's see what happens when we simplify the left side. Applying the distributive property, we get negative 6x plus 6x minus 3 equals negative 3, right? The left side simplifies to negative 3. These two terms add to 0. We get negative 3 equals negative 3. Now we can't stop there. We have to demonstrate that we understand the implication. When all the x's go away and we get a true statement, we have to conclude that there are an infinite number of solutions. Okay? We apply the procedure that we learned, the substitution method, and all the x's go away, leaving a true statement in this case. That the conclusion now is that there are an infinite number of solutions. Why are there an infinite number of solutions? Because the two lines are really the same. I often like to use the word disguise in this chapter. That what I did here was this second equation is really the first equation in disguise. It is an equivalent equation. Here's what I did. When I paused the video and went on to this system here, what I did was I took the y equals 2x minus 1. And recall in the previous system we had y equals 2x minus 1 and y equals 2x minus 1, right? But what I did for this one is, and this is why I'm not trying to denigrate what I teach. I love what I teach, and I think it's incredible and it's wonderful, but you can also kind of make fun of some of it in a positive, good-natured way. You can say it's a game. Somebody just rigged it for us. Well, what I did was I took this y equals 2x minus 1 and made a couple of algebraic manipulations. If I subtract 2x from each side here, we get negative 2x plus y equals negative 1. So what I've done is I've converted the slope-intercept form into standard form. But then, to disguise it a little further, I multiplied the entire equation by 3. So I went like this, and that's something we do in the elimination method, right? And if you multiply this entire equation by 3, you get negative 6x plus 3y equals negative 3. So this is negative 6x plus 3y equals negative 3 is the same line as y equals 2x minus 1. You might not have recognized it because it was disguised. And that's how this game is played, partly. Let's look at another situation now. Here is another system of linear equations. Notice, just for fun, I kept one of the equations the same as in the previous system, y equals 2x minus 1, but now we have along with it y equals 2x plus 3. Let's sort of ignore our understanding of Chapter 4 and parallel lines. You should be thinking about parallel lines. But let's ignore that for the moment and just go straight forward ahead with the substitution method in Chapter 5. And if y equals 2x minus 1, this 2x minus 1 can be put for that y there. 2x minus 1 equals 2x plus 3. Now, this equation can never produce a true statement. No matter what we put in for x, here and here, we will never get a true statement. If we followed our training for solving equations like this, we would subtract 2x from each side and then be left with that false statement. And when we're dealing with just an equation in x and not thinking about lines, we have to say at this point, well, there's no solution. There's no value of x that will make 2x minus 1 equal to 2x plus 3. The 2x plus 3, by the way, will always be how much bigger than the 2x minus 1? You should be able to answer that question. Not only can we say that these two quantities here are never equal, but we can be more specific than that. Can't we say that 2x plus 3 will always be 4 greater than 2x minus 1? Think about it, it will. And by the way, I just realized that in the previous system, when we had 2x minus 1 equals 2x minus 1, if 7th graders encounter that, and again, they follow their training, they would subtract 2x from each side, get negative 1 equals negative 1, a true statement, and then have to conclude that there are that any real number x will work. No matter what x is, 2x minus 1 will always be the same as 2x minus 1. It's an identity. I neglected to go through that in the previous one. But there's a little bit of subtle distinction or an additional understanding that we get when we're thinking of this as a system of linear equations. Of course, we're going to subtract 2x from each side and be left with the false statement that negative 1 equals 3, but you can't stop there. What you have to do is, recognizing that it's a false statement, you have to say that there's no solution. And that's really the same thing that a 7th grader would have to conclude if it's just this equation and not the system. But what we now have to understand is, why is there no solution geometrically? Well, it's because the two lines are parallel and distinct. They're not the same line like before when we had y equals 2x minus 1, y equals 2x minus 1. The two lines had the same slope of 2, but in addition to that, they were the same line. So here, they really are two distinct lines with the same slope. Therefore, they are parallel and no solution. There's no point of intersection. And of course, graphically, what we have, I'm just going to make a really rough graph. I have to try to make two lines that have a slope of 2, so they're going to be a little bit steep. One of them will go through the y-axis at negative 1, and the other will go through the y-axis at 3. And having a slope of 2, they might look, that's not steep enough, I don't think. You know, I could go, let's see, over 1, up 2, so maybe more like that, and like that. So two distinct lines. Why are they distinct? Well, because they have different y-intercepts. That's an easy way to see that they're not the same line. But they have the same slope, so they're parallel, therefore they don't intersect, therefore no solution to the system. Let's consider that notion of disguise again. Let me let you in on the secret right from the start. You may recognize negative 6x plus 3y equals negative 3 because I did the same thing that I did before with the y equals 2x minus 1. I subtracted 2x from each side and then multiplied each side by 3. So Whoops. That's not right. I was stuck in the last system. So sorry about wasting a little bit of time there. What I really need to do here is, I'll do a similar thing as I did before. Subtract 2x from each side, and then multiply by 3. I forgot, I was still stuck in the last system. Sorry about that. Now multiply by 3. Negative 6x plus 3y equals 9. All right, so this is a very simple matter to go from y equals 2x plus 3 to negative 6x plus 3y equals 9. It just involved 2 steps, right? Make sure you see how those 2 steps went. And again, what I'm trying to work into this video is getting inside the mind of the person that's creating the problem and understanding it from the teacher's point of view. If you can understand a problem from the teacher's point of view, you're obviously going to do very well in a topic, right? So let me erase that and say that this is our system. But of course, it's the same as y equals 2x minus 1 and y equals 2x plus 3, because this is equivalent. This is y equals 2x plus 3. Those are the same 2 lines. This and this are equivalent equations, therefore the same line. All right, so substitute. Put the 2x minus 1 in for the y down here. That we're given this and this, and we're asked to solve, so we'll go ahead with substitution, and we'll get negative 6x plus 3 times 2x minus 1 equals 9. Applying the distributive property, we get negative 6x plus 6x minus 3 equals 9. On the left side, 6x, negative 6x plus 6x is 0. These go away and leave us with negative 3 equals 9. This is a false statement, so we conclude that there is no solution. There's no value of x that we can put here and here to get a true statement. What does that mean geometrically? Well, it means we have 2 parallel lines, just like before, except it was a situation that was more in disguise than it was before. So we're going to call it quits there. This video started with a couple of looks back to Chapter 4, understanding some things from Chapter 4 in terms of Chapter 5, in terms of systems of linear equations that had a single solution. Recall the x and y intercepts of a line can be understood as a system of linear equations that has a single solution, a point of intersection, where one line intersects the y-axis or where it intersects the x-axis. And then we even looked at, any point like negative 3, 1 is the solution to a system of linear equations, where you have the vertical line x equals negative 3 and the horizontal line y equals 1, and the point of intersection is that point. So we looked at those 2 sort of special situations where there is a solution. And then we got to the special systems that Chapter 5 talks about, where you either have an infinite number of solutions because the 2 lines are really the same line. Now, and then you have the other situation where you have 2 parallel lines, and parallel lines do not intersect, so there's no solution. So either an infinite number of solutions or no solution. Those are the 2 special systems that are in Chapter 5. I just want to point out some commonality, right? In those 2 special systems where you have really the same line in disguise, or where you have 2 parallel lines. In either of those situations, the slopes of the 2 lines are the same. The slopes of the 2 lines are the same in case they are the identical line. If it's the identical line, obviously, same slope. And then if you have two parallel lines where there's no solution, two distinct parallel lines with no solution, then they have the same slope. So that's really what sort of creates those two special situations, is where the slopes of the two lines are the same. And we're going to explore that in a little bit more sophistication that's not in your textbook, something that I've picked up along the way, and that'll be the topic of a future video. So take care for now, 8th graders, and enjoy linear equations and their graphs, Chapter 4, and systems of linear equations, Chapter 5. Bye-bye.